Right. Today we are going over exponential change and separable differential equations. Okay, first let's go over exponential change. Often, when modeling real-world situations, a quantity increases or decreases at a rate proportional to its size at a given time. This is what we call exponential change. We can make such situations into an equation using y as the quantity that is changing and t as the time variable. Often, we call the amount present at t equals 0 y naught. And using these parameters, we can solve an initial value problem called a differential equation. And in this situation, our differential equation is dy over dt equals ky given, oops, given that y equals y naught when t equals 0. Okay, so if y is a positive number and increasing, then k is also positive. But if y is a positive number that is decreasing, k is negative. The function y equals 0 is a solution to the differential equation when y naught is equal to 0. But oftentimes, y naught is not 0. So to find the solution to our equation when y naught is not equals to 0, we divide the equation by y and integrate. And this looks something like this. So we start with our differential equation, dy over dt equals ky, and we divide both sides by y, which is the same as multiplying by 1 over y. Then we end up with 1 over y, dy over dt is equal to k. Then we integrate both sides with respect to t, so it becomes the integral of 1 over y dy dt equals the integral of k dt. And then using our integration techniques, we know this is the natural log of the absolute value of y plus c equals kt plus c. And so we want just the y on the left side, so we're going to subtract our c and our c. We're going to get natural log of y equals kt plus c still. That's because c is an arbitrary constant, so when we subtract an arbitrary constant from an arbitrary constant, we still end up with an arbitrary constant. So then, to get rid of the natural log around the y, we raise both sides by e. So it becomes e to the ln natural log or absolute value of y equals e to the kt plus c. And so when we have e to the ln of something, the e to the ln cancels out, and we just have the something inside the natural log as what it's equal to. So we have the absolute value of y equals e to the kt plus c. And remember, uh, exponents adding together, the kt plus c, is the same as e to the kt times e to the c. So we're going to rewrite this as the absolute value of y equals e to the c times e to the kt. And so to get rid of the absolute value is the same as plus or minus, or is similar to plus or minus. So we're going to put a plus or minus on the right side of the equation and get rid of the absolute value. So we're going to get y equals plus or minus e to the c times e to the kt. So e plus or minus e to the c is kind of a lot. So we're just going to write plus or minus e to the c equals the letter capital A. So we're going to get the equation y equals a e to the kt as our general solution. However, since we know that y is equal to y naught when p is equal to 0, we can substitute this information into this equation. So we're going to put y naught for y equals a e to the k times 0 because t is equal to 0. Anything to the 0 is 1, so this becomes y naught equals a. So our general solution for exponential change becomes y equals y naught e to the kt because we just switch this a with y naught because they're equal to each other. Okay, so when deriving our general equation for an exponential change, we had to solve a differential equation, which is what this was, so dy over dt equals ky. This one was pretty easy, but usually differential equations that we encounter are of the form dy over dx equals f of x, y. So this means that f is a function of both x and y. And a solution to such an equation is a function y equals y of x, where dx of y of x, which is the same as saying the derivative of y of x equal to f of x, y. Okay, so finding this solution may seem daunting at first, but it's actually not that bad. So let's say we have the differential equation dy over dx equals g of x times h of x, where g of x is an expression with only x as the variable, and h of y, this should be h of y, not h of x. H of y is an expression with only y as the variable. So what we want to do next is collect all the y factors on one side and then all the x factors on the right side. So what we're going to do is, we're going to divide both sides by 1 over h of y, and this becomes 1 over h of y times dy dx equals g of x. This is similar to what we did before, right? And so now we are going to treat the dy dx as a fraction, and we're going to multiply both sides by dx. So we're going to multiply by dx, and this will become 1 over h of y dy equals g of x dx, right? And now we have something in terms of y with a dy on the left, and then something in terms of x with a dx on the right. So what do we want to do? We want to integrate both sides, right? So it's just going to be the integral of 1 over h of y dy equals the integral of gx dx. And unfortunately, these are arbitrary equations, so we can't really integrate that, but we can do an example to see what this would look like in the real world. So let's say we have this example. Solve the equation y times x plus 1 dy equals x times y squared plus 1. So to solve this, we want to get all the y's on the left side and all the x's on the right side. So we have y times x plus 1 dy dx equals x times y squared plus 1. So we're going to divide both sides by 1 over y squared plus 1, and we're going to divide both sides by x plus 1. So this will become y over y squared plus 1 dy dx equals x over x plus 1. Then we're going to multiply both sides by dx, and that's going to get us y over y squared plus 1 dy equals x over x plus 1 dx. So now we're going to integrate both sides, right? So we take the integral of y over y squared plus 1 dy equals the integral of x over x plus 1 dx. So for the y over y squared plus 1 dy, we're going to do a u substitution, right? So u equals y squared plus 1, du equals 2y, so 2y dy, sorry. So we know dy equals 1 over 2y du. So we're going to have the integral. We're just going to look at the left side, just the y first. We're going to have y over y squared plus 1 times 1 over 2y. Oh, this should be y over u, because we're going to replace y squared plus 1 with u, times 1 over 2y times du, which is going to be, these y's are going to cancel out, and we're going to bring this 1/2 out to the front. It's going to be the 1/2 times the integral of 1 over u du, which is just equal to 1/2 ln absolute value of u, right? And so now we're going to do the x side. We have the integral of x over x plus 1 dx. We're going to do a little shortcut called plus 1 minus 1. We're going to do the integral of x plus 1 minus 1 over x plus 1 dx. So this will get us the integral of x plus 1 over x plus 1 minus 1 over x plus 1 dx, which simplifies to the integral of 1 minus 1 over x plus 1 dx, which is just becomes x minus ln x plus 1 plus c. Oop, we forgot the plus c over here, right? Oh, and then we're going to change this u to 1 half ln absolute value of y squared plus 1, right? And then these two sides are equal to each other, so we're going to rewrite the equation. We had y over y squared plus 1 dy equals integral of x over x plus 1 dx. This side was equal to this, so 1 half ln y squared plus 1. Now we're going to forget the plus c because we don't want that on the left side, equals x minus ln x plus 1 plus c. And that, I believe, is our solution to the differential equation. Okay, so now that we know how to solve differential equations, let's practice applying the exponential change equation to actual problems. So we're going to look at an example about yeast, which is a population growth problem. Let's see. Here we go. The biomass of a yeast culture in an experiment is initially 29 grams. After 30 minutes, the mass is 37 grams. Assuming that the equation for unlimited population growth gives a good model for the growth of the yeast when the mass is below 100 grams, how long will it take for the mass to double from its initial value? Okay, so we are going to use the equation y equals y naught e to the kt. Right now, we know that the yeast culture is initially 29 grams. That means that y naught is equal to 29, and that after 30 minutes, the mass is 37 grams. So we can use this information to calculate what k is. So after 30 minutes, the mass is 37 grams. So we know that when t equals 30, y equals 37. So we're going to plug that into our exponential change equation. We're going to get 37 equals 29, because that's y naught, e to the k times 30, right? So we're going to divide both sides by 29. This is going to become 37 over 29 equals e to the k times 30. And then we're going to take the natural log of both sides, which will become natural log of 37 over 29 equals natural log of e to the k 30. And when you have the natural log of something to an exponent, this exponent can actually go in front of the natural log. So this is the same as ln 37 over 29 equals k times 30 ln e, right? So, and then we also know that the natural log of e is just 1, so we have k times 30 equals the natural log of 37 over 29. Oh, that's just not 29. We're going to divide both sides by 30. We get k equals 1 over 30 times the natural log of 37 over 29, which is approximately 0.008118. Okay, that's our k value. So now we want to find how long will it take for the mass to double from its initial value? So its initial value is, that means we're solving for t, a time. Its initial value, y naught, is equal to 29. So double that is going to be, what is that? 58? Yeah, 58. 58. That's going to be our y value. So we have the equation y equals y naught e to the kt. So 58 equals 29 e, k equals 0.008118 t. Okay, we're going to divide both sides by 29 again. We're going to get 58 over 29 equals e to the 0.001, oops, 0.00818 t. And we're going to take the natural log of both sides again. ln 58 over 29 equals ln e to the 0.00818 t. And then we're going to skip a few steps because we did the same thing as before, but we're just going to go straight to 0.008118 t equals ln 58 over 29. And then we're going to divide both sides by 0.008118 and get t equals 1 over 0.008118 ln 58 over 29, which is approximately 85.38. So we know that it takes about 85 minutes to to double. There you go. Not too bad. Here's the full work if you want to look at everything that we did. Okay. So another way that the exponential change equation can be used in real life is to model radioactive decay. So the only thing that's different about this is that k is negative in these problems since our initial amount is growing smaller. That's why it's called decay. So let's look at a decay problem. Let's bring that in. So the decay of radioactive elements can sometimes be used to date events from Earth's past. In a living organism, the ratio of radioactive carbon, carbon-14, to ordinary carbon stays fairly constant during the lifetime of the organism, being approximately equal to the ratio in the organism's atmosphere at the time. After the organism's death, however, no new carbon is ingested and the proportion of carbon-14 in the organism's remains decreases as the carbon-14 decays. Scientists who do carbon-14 dating often use a figure of 5,730 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. Okay, so there are two things that we want to find here. The value of k and the value of t when y is equal to 0.9 y naught, or where y naught is the initial value. So 0.9 y naught just means that 90% of the radioactive nuclei are still present since 10% have decayed. So we want to find the value of k, right? To do that, we have a new equation just for these kinds of problems called the half-life equation. That is half-life is equal to the natural log of 2 over k. That means that if we multiply both sides by 1 over k, or sorry, by k, and 1 over half-life, which I'm just going to put HL, we get k equals ln2 over HL. So we know our half-life is 5730, so k equals ln2 over 5730, which we're just going to keep as that because it's a big number. Okay, so we want to find t when y is 0.9 y naught, or is 90% of what the original value was. So in this case, we have y equals 0.9 y naught, and that's also equal to 0.9. No, that's also equal to y naught e to the negative kt because k is negative, right? So we're going to ignore this part. We're going to have 0.9 y naught equals y naught e to the negative kt, right? And then the y naughts are going to cancel because they're on both sides. So we just get e to the negative kt equals 0.9, right? We're going to substitute our k in here. We're going to get e to the negative ln over, ln2 over 5730 t equals 0.9, right? We're going to take the natural log of both sides. We're going to get ln e to the negative ln2 over 5730 t equals ln 0.9. And same thing as before, we're going to end up with negative ln over 5730t equals ln 0.9. Oops, ln 2. We're going to multiply it by negative 5730 over ln 2. And then we're going to get t equals negative 5730 over ln 2 times ln 0.9, which is about 871. And so 5730 is in years, so this means it's 871 years for, yeah, 871 years is the age in which 10% of the nuclei have decayed. Okay, our final topic for today is heat transfer. So this is when an object's temperature changes due to its surrounding temperature. This can be modeled using an equation similar to the exponential change equation called Newton's law of cooling, which I'm going to write in purple because purple is cool. So Newton's law of cooling, Newton's of cooling is the equation H minus H sub S equals H naught minus H sub S e to the negative kt, where H is the temperature, temp at time t. H sub S is the constant temperature of the surroundings of the object. This is the temperature at time t of the object. And then H naught is the object's initial temperature. Okay, so let's do a problem with this. Okay, let's see what we want to do. We have a hard-boiled egg at 98 degrees Celsius is put in a sink of 18 degrees Celsius water. After 5 minutes, the egg's temperature is 38 degrees Celsius. Assuming that the water has not warmed appreciably, how much longer will it take the egg to reach 20 degrees Celsius? Okay, so what we know for sure is that H naught, the initial temperature, is 98 degrees Celsius. The surrounding temperature, HS, is 18 degrees Celsius. And yeah, that's all we know so far. So with the general equation, we get H minus HS equals H naught minus HS e to the negative KT. So we're going to put H minus 18 equals 98 minus 18 e to the negative KT. We're going to add 18 to both sides. We're going to get H equals 18 plus 98 minus 18 is 80, 80 e to the negative kt. So we also know that after 5 minutes, the egg's temperature is 38 degrees Celsius. So we know that H equals 38 degrees Celsius when T equals 5. And we can use this information to solve for K. So we're going to substitute 38 for H equals 18 plus 80 e to the negative K, and then T equals 5, so 5. Right, we're going to subtract 18 from both sides. We get 20 equals 80 e to the negative 5k. Going to divide both sides by 80. Oops, 80. We get e to the negative 5k equals 20 over 80 is 1/4. Right, we're going to take the natural log of both sides. So it becomes ln e to the negative 5k equals ln 1 over 4. And then same stuff as before. This is going to become negative 5k equals ln 1 over 4. Divide by negative 1 over 5. Then we get equals, and that becomes k equals negative 1 over 5 ln 1 over 4. So k is about negative, or I guess here it'd be positive, 0.28. Because then when we plug it into this equation, the negative sign's already there, right? So we want to see how much time it'll take for h, the object's temperature, or the egg's temperature in this case, to be 20 degrees. So we have h equals 18 plus 80 e to the negative 0.28 t. So in this case, h is equal to 20. 20 equals 18 plus 80 e to the negative 0.28 t. We subtract 18 from both sides. 2 equals 80 e to the negative 0.28 t. Divide both sides by 80. You get e to the negative 0.28 t equals 1 over 40. Take the natural log of both sides. Ln e to the negative 0.28 t equals ln 1 over 40. You know what to do. This becomes negative 0.28 t equals ln 1 over 40. Divide both sides by 1 over negative 0.28. Then you get t equals negative 1 over 0.28 ln 1 over 40. T is approximately 13 minutes. There you go. That's how long it takes for the egg to become 20 degrees Celsius. And yeah, that's all there is to this kind of stuff.